Welcome to the fifth part of thermodynamics, and in this part you will learn about thermodynamic state variables, indicator diagrams, thermodynamic state variables and equation of state. Every equilibrium state of a thermodynamic system is completely described by specific values of some macroscopic variables, also called as state variables. For example, an equilibrium state of gas is completely specified by the values of pressure, volume, temperature, and mass, and composition if there is a mixture of gases. A thermodynamic system is not always in equilibrium. For example, a gas allowed to expand freely against vacuum is not an equilibrium state. As shown in the diagram, the partition in the box is suddenly removed, leading to free expansion of the gas. During the rapid expansion, pressure of the gas may not be uniform throughout. Similarly, a mixture of gases undergoing an explosive chemical reaction, for example, a mixture of petrol vapor and air, when ignited by a spark, is not an equilibrium state again. Its temperature and pressure are not uniform because the diagram shows a mixture of gases undergoing an explosive chemical reaction. Eventually, the gas attains a uniform temperature and pressure and comes to the thermal and mechanical equilibrium with the surroundings. In short, thermodynamic state variables describe equilibrium states of systems, and the connection between the state variables is called equation of state. For an ideal gas, equation of state is denoted by PV equals to mu RT, or in some books it is also by nRT. The pressure volume curve for a fixed temperature is called an isotherm. The thermodynamic state variables are of two kinds. Extensive variables. They indicate the size of the system, which means extensive variables are those that depends on the mass of the system or the number of particles in the system. For example, volume, mass, internal energy. And intensive variables are those they do not depend on the size of the system. For example, pressure, temperature are the intensive variables. Thermodynamic processes. Quasi-static process. Quasi-static means nearly static. The system changes its variable pressure, temperature, and volume so slowly that it remains in thermal and mechanical equilibrium with its surrounding throughout. At average stage, the difference in the pressure of the system and the external pressure is infinitesimally small, and it is same for the temperature difference between the system and surroundings. A quasi-static process is obviously a hypothetical construct. In practice, processes that are sufficiently slow and do not involve accelerated motion of the piston, large temperature gradient, etc. The diagram shows a quasi-static process. The temperature of the surrounding reservoir and the external pressure differ only infinitesimally from the temperature and pressure of the system. Allow the system to equalize its pressure with that of the surrounding and continue the process infinitesimally slow until the system achieves the pressure P dash. Similarly, for the system till it achieves the temperature T dash. A graphical representation of the state of system with the help of two thermodynamic variables is called an indicator diagram. When a system undergoes an expansion from state A of pressure P1 and volume V1 to a state B of pressure P2 and volume V2, the indicator diagram for expansion is shown. And in case of compression, it will be reverse. Now at state A, the pressure P1 and volume V1 goes to a state B at pressure P2 and volume V2. You can see that both the diagrams are same, only there is a difference in the arrow. So take care of this one while plotting the graph. Isothermal process is that process in which the temperature remains constant throughout while all other variables change. And for an ideal gas, PV is equals to nRT. And as N is constant, number of moles for a particular gas are constant, R is constant, and in this case temperature is also constant. So PV will be equals to constant, and this is nothing but Boyle's law. Means pressure and volume are inversely proportional to each other. And also note one main point that in isothermal process, as there is no change in temperature, so internal energy for an ideal gas also depends upon the temperature, means there is no change in the internal energy. And from first law of thermodynamics, delta Q will be equals to delta W only. Graphically, if we plot pressure and volume curve, the curve you will obtain as shown, means if you will increase the pressure, volume decreases and vice versa. And this type of curve is known as isothermal curve.